In the previous video, we introduced the notion of a Cauchy sequence of real numbers, although in this video, we will allow ourselves to work with different sets. So just a quick recap, although I hope you have that definition fresh in your mind coming off of the previous video. We say a sequence is Cauchy if, given any choice of epsilon greater than 0, you can then find a threshold index capital N, so that when you take any indices, any pair of indices beyond that threshold, here I order them as m is greater than or equal to n is greater than or equal to the threshold, then the distance between their corresponding sequence terms is less than that number epsilon that you started with. Okay, so we worked through a couple examples of Cauchy sequences in the previous video. We also proved two results, both of which we will cite today. So we proved that Cauchy sequences are bounded, and we proved that if a Cauchy sequence has a convergent subsequence, then the Cauchy sequence itself is also convergent and to the same limit. So if you are starting this video and you haven't seen my first video on Cauchy sequences, please watch that one. We are going to continue talking about Cauchy sequences here. And in particular, what we are ultimately going to build up is the definition of what is called a complete metric space. Now, for real analysis 1, I really just focus on working with real numbers. So the goal today really is to say that the set of real numbers R is complete. However, it's like, what are you analyzing when you talk about completeness? Typically metric spaces. So let me just throw up here a quick definition of what a metric space is. This isn't something I'm going to talk much about in this course, but if you follow my real analysis 2, I spend like a ton of time on metric spaces in that course. So if you follow real analysis 1 and 2 with me, you will end up with a really solid understanding of metric spaces. But what is a metric space? In very basic terms, good enough for this course. A metric space is a set together with a suitable notion of distance. And all I'm going to say today is that our way of measuring distance between real numbers, so the absolute value of a minus b, is the distance between the points we associate with the numbers a and b on the number line. So this is a distance measurement. That is the kind of distance that will work in the definition of a metric space. Okay, so real numbers equipped with this distance measurement is a metric space. You could also work with, say, just where I'm looking at Q. Q, the set of rational numbers with the same distance measurements. And here I'm trying to mean like the absolute value notion of distance, so absolute value of a minus b. So Q with this distance measurement is a set with a suitable distance. That's a metric space. Similarly, we could just consider numbers strictly between 0 and 1 with the same notion of distance. So in this lesson, we will work with a couple different sets just to understand what it means to say that R is complete, like what's the power of that statement. But we won't work with any other notions of distance. Again, if you want to talk about metric spaces more in depth, I have a lot of videos on that topic. All right, let's go ahead and get going with this lesson. Here's our first firm statement making a connection between Cauchy sequences and convergent sequences. So in particular, in any metric space, that's the broadest statement I can make, if you know that a sequence converges to a limit L, so if you have a convergent sequence, then you have a Cauchy sequence. So every convergent sequence is Cauchy, always. And we're going to do the proof right now because it is the easiest proof in real analysis. This is the kind of proof that you should be able to do 30 years from now without too much thought. Like this is as good as it gets for real analysis. Okay, suppose that AN converges to L, and let's let epsilon be greater than 0. We already know that the sequence converges. So I can choose a threshold index out there so that the terms in my sequence beyond that threshold are as close to L as I want them to be. So choose the threshold capital N from the set of natural numbers such that whenever an index N is at or beyond that threshold, it follows that, I know it has to be, but I'm going to leave it blank again, just illustrating what it looks like to trust that a proof will work out and then fill in the missing information. So A sub n minus L would be less than, in the traditional statement, you would write epsilon, but I'm going to leave it blank for now, and we will work out what that has to be in a minute. Let's consider any pair of indices beyond this very same threshold capital N. Choose any M and N. I'll just say pair of indices greater than or equal to N. Maybe I'll make it clear that M is also greater than or equal to N. And notice, all right, for this threshold that we've already identified, because we were given a convergent sequence, I'm now going to take two terms beyond that threshold and see how far apart they are relative to each other. So we want to pass from this kind of statement, measuring sequence terms off the limit, to measuring them off each other. And this is why I say it's the easiest proof in real analysis, because we've done this before. So if this was the first time we've done this, I wouldn't call it the easiest proof ever. But here, I want to compare these two terms to each other. What can I compare them to individually instead? So do they have a mutual friend? And just look at the line above. L should be what we compare each of them to. So let's subtract and add back L, like that. We saw this kind of computation in a previous video, the previous video. So we have two pairs here inside of a single absolute value computation. This is, again, why the triangle inequality is so fundamental, is that we often bring in this kind of comparison, because to get from here to here might be challenging, but you can go through an intermediary. In this case, that's the limit L of this convergent sequence. So let me go ahead and break this up with the triangle inequality. Here it's L minus AN. That's what I could write here. L minus AN, which is fine, but to make it look more traditional, if you factor out a -1 and compute its absolute value, you'll realize that that is the same thing as writing the absolute value of AN minus L. All right, I want to have both of these sum to something smaller than epsilon. Go ahead and wrap up the proof. What do I need to write here in order to get from this to epsilon? Epsilon over 2. And we are done. Okay, so rereading this from the beginning, we were given a convergent sequence as our hypothesis, and that is very powerful because it's a limit. Like, we know that there's a limit for the sequence that we can compare terms to. So when we compare terms to each other, we go through the limit, use the triangle inequality, recognize that we're just going to have two things here. So if we ensure that both of these individual distances are smaller than epsilon over 2, adding them together produces something smaller than epsilon, and therefore this tells us that our original sequence is Cauchy. Actually, before I erase this, let me just mention that I proposed this theorem for any metric space, and the proof works for any metric space. However, because we are interested in real numbers, I am specifically here working with our distance measurement that looks like this. So our traditional distance between real numbers. If you were working with a different notion of distance, you would have logically the exact same proof. So the exact same bound here, the exact same triangle inequality argument. I just wanted to mention that because distance is not always designated with this absolute value computation. Now let's look at the converse for real numbers, sequences of real numbers with our typical distance measurement on the number line. This says that if a sequence is Cauchy, then it converges. So we're just reversing the roles of the previous statement. Notice here that I did not say in any metric space. I'm specifically here talking about real numbers, sequences of real numbers. All right, this proof can be very heavy, meaning it's possible to watch someone prove it or read a textbook proof of this statement that takes like 1 to 2 pages. Ours will be 4 sentences because of the work that we've already done. So I will just cite 4 earlier results to get exactly what we need. So it's shockingly short, but a lot of work went into those 4 citations. So, what's difficult here? Maybe I should start there, since the proof itself is not going to seem that difficult. We know that the sequence is Cauchy by hypothesis. To show that it's convergent with no other information, it feels like I need to identify a limit L. How on earth could you find the limit L for the sequence? We don't have a specific sequence. I don't know how to choose L, right? This is a general statement. So that's what's really hard, is to prove this statement, you need to bring in a real number L and prove it will work for the sequence without having any kind of actual specific terms here. So there are different ways to do this. Our way is, I think, the easiest, which is, again, 4 lines. It's a 4-line proof. You'll clearly see the moment when we find the L. All right. The reason why not everybody has such a short proof for this statement is not every course or textbook covers the monotone subsequence theorem, but we did. So by the MST, so that's the monotone subsequence theorem, this Cauchy sequence must have a monotone subsequence. Which I will name A sub n sub k. Okay. Every sequence of real numbers has a monotone subsequence. This is a sequence of real numbers, so it has a monotone subsequence. The first result we proved in the previous video was that all Cauchy sequences are bounded. Well, this is consisting of terms from the original sequence, so this sequence is bounded in its own right. So let me just say prior video. Since the original sequence is bounded, so is the subsequence. We know that, let me write, since an is Cauchy, okay, it's going to be 5 sentences because this is going to be 2. Thus, A and K is bounded. BDD is my abbreviation for bounded. All right, next step is yours. We have a monotone sequence which is bounded. So go ahead and write down the most natural feeling third statement that we should make here. Hopefully your mind went to the monotone convergence theorem, which tells us that every bounded monotone sequence of real numbers, like what we are working with, converges. So not everybody necessarily covers the MST or emphasizes it. You should cover the MCT in any analysis course. So by the monotone convergence theorem, there exists a real number L such that this monotone and bounded subsequence, here's the boundedness of the subsequence, converges. Okay. So our bounded monotone subsequence converges, therefore it converges to some limit, and this is the introduction of L. So just from the start, we had no idea where the limit was going to come from, and now we're saying, well, we actually can figure out that this Cauchy sequence must have a convergent subsequence. Let's name its limit L, and then that's how we bring the limit into this proof. Okay, we just have one more thing to say. Again, it depends on something from the previous video. See if you can wrap up this proof. The second statement that we proved about Cauchy sequences in the previous video was that if a Cauchy sequence contains a convergent subsequence, then the original sequence converges to the same limit. I actually treated that like just an exercise in the previous video. I apologize if I undersold it because here we're about to cite it in this very important result. So by the prior video, since an is Cauchy, and it has a subsequence converging to some limit, the entire sequence converges to the same limit. All right. So let's just read back through this together. By the monotone subsequence theorem, telling us that any sequence of real numbers has a monotone subsequence. This is a sequence of real numbers, so it has a monotone subsequence. Nothing about being Cauchy there, it's just about being a sequence of numbers, real numbers. And then since it's Cauchy, we proved in the previous video, we did a proof that it's bounded. And since this is consists of terms from the original sequence, this is also bounded. Anytime you are working with sequences of numbers and you see the words monotone and bounded, you should think about the MCT. So that should come to you as soon as you start seeing those adjectives. So by the monotone convergence theorem, the bounded and monotone subsequence converges. Knowing it converges allows us to write down an explicit limit. We're just going to name it L. And then in the previous video, we proved that a Cauchy sequence with a convergent subsequence also converges. Okay, so this was a pretty short proof, but we cited 4 results, each of which needed a full proof on its own. There are other ways to get to what's called Cauchy completeness of R. So this result, sometimes it's called the Cauchy criterion for real numbers, that every Cauchy sequence converges. It's the Cauchy completeness of real numbers, talking about Cauchy sequences converge. It can even be used as an alternative to the supremum property to give us that completeness axiom. If you think back to the very first or second video in this course when I went through the axioms of real numbers, we had this notion of completeness. We're about to define completeness. We actually haven't yet, but this is a big result. I think I will do a separate video where I talk about maybe alternative paths through this material, because I have done this by building up monotone subsequences and the monotone convergence theorem. This was the route I took to get to the fact that Cauchy sequences of real numbers converge. There is another common path which would first introduce something called the Bolzano-Weierstrass theorem and then use it in a also fairly short proof, because the Bolzano-Weierstrass theorem itself would need a lot of support. I haven't done the Bolzano-Weierstrass theorem. We're actually going to prove that as a consequence. So actually, we'll prove it a couple different ways. I don't want to get off topic. Basically, in real analysis, there can be multiple paths through this material depending on how you start your axioms and then how you build off of them. And so this was how we built up to this result. It's quite possible, if you're reading through a textbook, that it will take a different but equally valid route. I've thrown the word complete around a few times, but now I am ready to state its actual definition. We saw that every convergent sequence is Cauchy, always. We just proved that sequences of real numbers which are Cauchy also converge. So it feels like the two concepts, convergence and Cauchiness, are synonyms, but that's not generally true. If it is true, then the space that you are working in is complete. So in particular, because Cauchy sequences on the real number line, equipped with our usual Euclidean notion of distance, converge. So Cauchy sequences of real numbers converge. That is exactly what is required in order to say that the set of real numbers is complete. So completeness happens for a space when being Cauchy is equivalent to converging. You might not recognize that as special until you see that it doesn't necessarily have to happen. So here, I've given you 2 alternative worlds to imagine living in. Suppose instead of working with sequences of real numbers, we lived in a world where there were no irrational numbers. So we worked in the metric space consisting of the set of rational numbers together with our standard notion of distance. So the absolute value of a minus b is the distance from a to b in this new world. Can you devise a sequence of rational numbers which is Cauchy? That might just be something that you kind of eyeball in this moment, but does not converge in this world. So is it possible to write down a sequence of rational numbers which is Cauchy but not convergent in the metric space consisting of just rational numbers together with our standard notion of distance? And let me go ahead and pose the second question as well while we're here. Same question, but this time imagine that we live in a world strictly between 0 and 1. So can you write down a sequence which lives in this metric space? So the numbers between 0 and 1 with our standard notion of distance. You want a sequence which is Cauchy, but not convergent in this world. So see if you can do that, and then I will come back and give you probably 2 examples for each. For a first example of a sequence of rational numbers which is Cauchy but does not converge in the world of rational numbers, consider, not this number, 1 second. Consider the sequence that looks like 3. That would be my first term in the sequence, and then 3.1, 3.14, 3.141, and I only know that far in the decimal expansion of pi. Each of these is a rational number because they are decimals which terminate. So this is a sequence of rational numbers. I know it's Cauchy. You could get to that maybe 2 different ways. Take any epsilon greater than 0 and take in large enough so that all terms beyond only differ like after 100 decimal places and make that enough to be smaller than epsilon. That was kind of lazy, but that's the idea. Alternatively, to know that the sequence is Cauchy, what you can say is, well, if this were viewed as a sequence of real numbers, it would converge to pi. Since it converges as a sequence of real numbers, it's Cauchy as a sequence of real numbers. But then it must be Cauchy as a sequence of rational numbers because that's just pairwise distances between the terms in the sequence. So if distances between these numbers get very small with when they're viewed as a subset of real numbers, they will also get equivalently small when viewed as belonging to the set of rational numbers. Okay, so since this sequence is a convergent sequence of real numbers, it's a Cauchy sequence of rational numbers. And it wants to converge to pi. But this is not a valid limit in the world of rational numbers because that's not a rational number. So it's like the set of rational numbers has a hole in it, which is what the sequence is trying to approach to. So it's not what you might call like a continuum, like R is. We're getting closer and closer and closer to something, but that something does not belong to the set of rational numbers. So this is a Cauchy sequence which does not converge as a sequence in Q with the normal metric space. Sorry, the normal notion of distance. So what you could write is Q together with this notion of distance is not complete. And that's all you need is one counterexample. But if you're watching this, you like math, so let me just remind you of another sequence of rationals. And this one I'll give you an sorry, 1 second. This one I will give you an explicit form for. Let the nth term in the sequence be 1 plus 1 over n to the n, like that. For each n, this is a rational number, and then we're exponentiating it to an integer. So you might have something like 1 plus 1 over 3 cubed, so that's just a finite product of rational numbers. This is rational. Again, it's easier to analyze this sequence if we instead kind of embed it on the real number line and think about what it would do as a sequence of real numbers. Do you know what this sequence is converging to? It's a very famous limit. It's converging to the number e. Okay. So this is a sequence of rational numbers converging to e. I just wanted to remind you of this definition in case you haven't seen it before. So e is the limit of that expression as n goes to infinity. Since as a sequence of real numbers it converges, it must be Cauchy. The pairwise distances between the terms in the sequence must be getting very small as we go out further and further in our sequence. So it's Cauchy. It's a sequence of rational numbers, but it is not a convergent sequence in this metric space. So again, this is not a complete metric space. All right, what about a sequence between 0 and 1? This might be even easier if you think about trying to drive a sequence to either 0 or 1, which do not belong to the set. Let me just do this 2 different ways. It's easy to actually bounce out of the set. So let me do something like a half, a third, a fourth, a fifth, right? We actually proved that a sequence of this form is literally Cauchy. So we wrote down a formal definition or formal proof of the Cauchiness of this kind of sequence in the previous video, and it did not rely on living in the world of real numbers. So you could prove manually that this is Cauchy without too much difficulty, or you could say, hey, this really wants to converge to 0 on the real number line, but that's not in the set. So this is Cauchy, but does not converge. Like that. And again, that's enough. One example of a Cauchy sequence which fails to converge in a metric space is enough to know the metric space is not complete. Or if we wanted to, we could do something like pi over, I just have to make sure, let's do n plus 2, 3. I think that will land us between 0 and 1. I had to make sure the first number was smaller than 1. That was my hesitation, because pi divided by 1 is pi. So this is very similar. It's being driven closer and closer to 0. So it's trying to converge to 0, and it would converge to 0 if it were viewed as a sequence of real numbers on the real number line. So it's Cauchy, but again, the limit it wants to approach does not belong to this metric set. metric space. And the reason I just mentioned this is because this is a sequence of irrational numbers. So if you looked at just irrational numbers, you would also come to the same conclusion that it's not complete. Okay, so those two metric spaces, the set of rational numbers and numbers between 0 and 1, equipped with the same notion of distance that we've been working with, they are not complete metric spaces. R is special in that way. R is complete. It has no holes. How you can think of that is like every kind of limiting behavior that you could imagine having will limit to something on the set of real numbers. So every choice of limit does live on the number line. It's complete. There's no holes. We can't approach something, but fail to approach something that exists, which is what we're doing here. Okay, I don't want to say too much more about this. I did want to get to the statement that R is a complete metric space. I think I will step away for just a moment so that you can think about this. And I also want you to try to come up with at least one answer to the question I have down here on the bottom, which is, especially if we're just studying real numbers where being Cauchy and being complete are equivalent, it turns out. Do we even need Cauchy sequences? So what's the point of having this kind of, for real numbers, alternative characterization of convergence? This is just a thought experiment, so there might be many ways to think about this question. Let me give you 3 responses. One response is that it gives us a notion of closeness that does not require a limit. And that would actually be valid in these metric spaces. So we might want to be able to say that the sequence consists of terms getting closer together, a sort of clustering behavior, without requiring those terms to have an actual limit. So again, it's another way of describing closeness. In fact, sometimes you might be wanting to prove convergence, but you can't find the limit L. That's often the case when you're working with series expressions, right? So we haven't talked about series of numbers formally yet together, although we will. But I'm sure in some kind of calculus course that you talked about series of numbers. And we have all these tests, p-tests, ordinary comparison tests, limit comparison tests, et cetera, because it's possible to be able to say that a series of numbers converges without being able to say what it converges to. And when we study series, we will bring in the fact that we can perhaps show that their sequences of partial sums are Cauchy, and that way we can know convergence happens without ever needing to name a limit, because perhaps we cannot do so. So you can have convergence but not be able to compute the actual limit. And Cauchiness gives you a way to address that. And then also, the statement, which is always true, is that convergence always implies being Cauchy. The definition of a convergent sequence is one that identifies a limit. And if you want to prove that it is failed, it can be tricky because if you want to prove that a sequence diverges, you can't show that every single possible number that exists can't work in the definition because there are uncountably many possible limits that are going to fail. So you can't write uncountably many proofs, etc. However, perhaps you can show that the divergent sequence in question is not Cauchy. And the contrapositive of this implication is not Cauchy implies not convergent. So proving a definition fails can be challenging. Proving literally that a sequence fails to be convergent just using the definition might be hard, but perhaps you can show that instead it is not Cauchy and therefore it is not convergent. Okay. Just thinking of explicit sequences, I can't come up with a good idea for that or a good example off the top of my head, but I know that comes up sometimes for me in real analysis 2 in particular. So there will be moments in real analysis 2 where I'll say, hey, look, the sequence is not Cauchy, so it's not convergent. So the contrapositive of this implication can be useful. Okay, I have one more thing I want to do before we wrap up this lesson, and that is just an exercise in analyzing a proof and the truth of a proof. I want to revisit our proof that Cauchy sequences of real numbers converge by thinking about why the proof would not work for this metric space or this one. So we just had a kind of 4-line proof. So there's just 4 lines for us to think about, or 4 statements for us to think about. Which ones will fail when we replace R with either the set of rational numbers or the set of numbers between 0 and 1? Now that we have seen examples of Cauchy sequences of rational numbers, as well as Cauchy sequences of numbers between 0 and 1, which fail to converge, let's read through this proof again and see where they would break down for those alternative metric spaces. So take a moment to read through this proof and decide which of these kind of 4 lines are valid for Q, or the open interval from 0 to 1, and which ones can we not apply. So why does this proof not work in those metric spaces? I love this kind of exercise. So seeing why proof that works in one context does not always work in other contexts. Let's do this line by line. The monotone subsequence theorem said that any sequence of real numbers must have a monotone subsequence. If I take a sequence of rational numbers, that is also a sequence of real numbers. So if I go from Q to R, in that world, I could extract a monotone subsequence. But that monotone subsequence would be a subsequence of my original sequence. It would be a subsequence of rational numbers. So we could just go back to Q. So any sequence of rational numbers would have a monotone subsequence. Likewise, any sequence of numbers between 0 and 1 is also a sequence of just real numbers. So it has a monotone subsequence, which is a valid subsequence of the original sequence between 0 and 1. Okay, all that to say that this line would still work if we were trying to prove that Cauchy sequences must converge in those other 2 metric spaces that we just looked at. Think about being Cauchy in those spaces. Would it apply being bounded? And the answer is yes. You could think about this maybe 2 different ways. One is just to go back to the proof that we wrote down in the previous video and see if it ever depended on being really on R, or would it still work if we were just on Q or between 0 and 1? And you should find that the proof actually didn't require us to have the entire set of real numbers. The other is, again, to think of Q, the set of rationals, and the numbers between 0 and 1 as embedded on the whole real number line. A sequence of rational numbers, which is Cauchy in Q, is also Cauchy in R, so it's bounded in R, but then just go back down to Q, it's bounded in Q. So this works, which means that the subsequence we've already found is also bounded. What about this third line? Is it necessarily the case that our bounded and monotone subsequence, which we still have, must converge to L? In other words, does the monotone convergence theorem apply to the set of rationals with our notion of distance, or the numbers between 0 and 1? And the answer, of course, is no, because actually, if you look at the examples we did, like decimal approximations of pi, or the sequence of numbers of the form 1 over n plus 1, those were bounded and monotone sequences. They wanted to converge, but they had to converge outside of the space. So this does not work. The monotone convergence theorem is a theorem about sequences of real numbers. And in fact, now that we've talked about like completeness and this idea of kind of filling in the number line, if you have a sequence which is, say, monotone increasing and bounded, yeah, it wants to converge to something, but the ceiling that's kind of emerging from my picture has to live in the space. And by the supremum property, that was our axiom that kind of gives us completeness on R, so we use that here. On R, our supremum property placed this horizontal line in the metric space that we're working in. It's a real number. But if this were decimal expansions of pi and this line were pi, there's no guarantee that that's going to be a rational number. Or if it's numbers getting closer and closer to the number 1, but 1 does not belong to the space, right? So this idea of like approaching doesn't quite work when we pass from R to Q to rational numbers, or from R down to just the open interval between 0 and 1. Okay, so this is where the proof fails, but let's go down to the 4th line anyway, just for fun. If it were the case that we had a Cauchy sequence of rational numbers, and that sequence had a convergent subsequence, would our sequence of rational numbers also have to converge? And the answer, I hope you realize, is yes. And if you go back to that proof, there was a triangle inequality argument, you'll recognize that nothing about that required, having all real numbers like this, drawing this line does. Okay, so this third line, the monotone convergence theorem here is what's really special. So this is really what's giving us the ability to apply this proof to real numbers, but not to rational numbers or the open interval between 0 and 1. Okay, I'm ready to wrap up this second look at Cauchy sequences. As I mentioned a little while ago, I said the words Bolzano-Weierstrass, and if you're following my course, you haven't maybe heard that expression before. That's what's coming up next. Thank you for your attention.